Hi everyone, welcome to this video where we'll discuss the channel pruning model compression technique in AIMET. My name is Abhi Khobre. I'm from Qualcomm AI Research. AIMET stands for AI Model Efficiency Toolkit. AIMET is an open source library brought to you by the Qualcomm Innovation Center. In this video, we'll talk about model compression using this technique called channel pruning. I hope you have had a chance to look at the spatial SVD model compression video, which is also part of the series. I think there are quite a few topics in that video that are applicable for this video, and I'm not going to repeat that, so I would strongly suggest you see that one first before watching the channel pruning one. So having said that, I think this video will be a much smaller video. So let's dive in. So channel pruning is another model compression technique, and specifically what this does is it takes layers and sort of removes some channels from those layers, let's say unimportant channels, and then it makes changes to the graph to to account for this change. And so we'll look at some of the details. So there are three different steps in channel pruning. So first is channel selection, meaning what channel should we remove. Second step is called winnowing, which means now that we remove these channels, what other changes to the graph do we need to do to still have the graph be consistent. And then the third part is called weight and bias reconstruction. And here what we're going to do is we're going to use linear regression to do some updates to the weights and biases so that we still see good accuracy at the end. Okay, so let's look at each in a little bit of detail. So channel selection is actually fairly simple. So what we do is given a layer, we are just simply looking at the magnitude of each channel, and we choose the channels which are the least magnitude. Okay, and how many channels are picked is depending on the compression ratio selected for that layer. Winnowing is the next step, and winnowing, so I think this picture is just showing that you started out with, in this particular layer, with 32 input channels, and some of the channels were removed. In this case, I think 2 of the channels were removed. So you went from a convolutional layer with 32 input channels, and it resulted in 30 input channels instead at the end. Note that nothing else has changed really. So, however, let's, for example, this was the layer over here, right? So layer 3 was the layer in question. So we removed 2 out of 32 channels from this layer. So to make this graph work, what's going to happen is if you don't do anything else, the output of this ReLU batch norm / ReLU is going to mismatch with the shape of the input required for this layer, and it's just not going to work. So to make this graph consistent, we need to see which other layers we need to change. So we would have to change, let's say there was a batch norm and a ReLU, we'd have to change those layers and change their remove the corresponding channels from those layers. Also, we go up to this convolutional 2D layer and we will have to change its output channels, right? The corresponding output channels corresponding to the input channels we removed here, we have to remove the output channels over there. And once we have made these set of changes, then you could argue that the graph is consistent, because any layer above this is still dealing with the channels, number of channels that are fed into this layer, so nothing else changes. So this whole process we call winnowing, and it's actually fairly involved because we need to understand the whole the graph for this particular model, and whether the graph has splits, and adds or concats, and those come into play when we are making a decision. Okay, so let's move on to the last step, which is called this weight reconstruction. So since we, sort of removed channels across these layers, we are essentially throwing some of the features out, right? And generally, this is a much more aggressive change to the network as opposed to what we did for spatial SVD. So you would see like a drop in accuracy just due to this. So to counteract this and to have the model not completely break down, we use this weight reconstruction method. And what's happening here is what we would do is we would take original unpruned model, and then we would take this compressed model. And let's say layer 3 is the layer in question where we have pruned this layer. So we would take the expected output from the original model, and we would take the input from the new model, and we would try to sort of linear regress from this input to that output with respect to the weight of this layer. And so the weights get updated based on this linear regression. And this helps to recover some of the accuracy back. Of course, this is not intended to be a replacement for fine-tuning. So after you're done with all of this, you would still take that compressed model, use a training pipeline, and run it through the training pipeline for the fine-tuning. And again, we don't need all the epochs that we would have needed to train from scratch. We would use a fraction of the epochs, generally around 10 epochs or so. The model will recover most of its accuracy back. Any further epochs of training you do has diminishing returns at that point, but you'll still see some increase, and it all depends on your particular model, how many epochs of fine-tuning you would need. So one additional thing I would like to add here with respect to winnowing is sometimes like we looked at an example where we pruned this input channels of this layer, and we were able to modify the output channels of this layer and suffice. However, there are more challenging situations. So for example, if we wanted to remove the input channels of layer 2, now this is a much more difficult problem, because if you look at it, we can't just simply remove the output channels of this layer, because the output channels of those layer also feed into this residual into this element-wise add, and the shapes are not going to match up here. So in this kind of case where we are trying to prune input channels of a layer that is below a split point, what we could do is we could add a downsample layer in front of this layer. And that would just simply, take the, let's say 32 channels coming in, and this wanted to remove 2 of those channels. The downsample would simply discard those 2 channels before feeding into this layer. And, from a perspective of compute, it is still perhaps a good thing to do, because a downsample operation, if done correctly, would not be compute intensive, whereas you would get some savings by removing channels because of the multiplicative effect in a convolutional layer. Okay, so having said that, let's jump into the code. So before we jump into code, let's look at the APIs for channel pruning. And if you look at the overall compressed model API, as we know that this API is actually shared between spatial SVD or channel pruning or any such pruning techniques. And so you just simply choose what compression scheme you want, whether it's spatial SVD or channel pruning. So you just choose the scheme, and then you choose basically, so here you will say channel pruning, and you would choose the parameters corresponding to that. So let's take a look at what are these channel pruning parameters, right? So the auto mode channel pruning parameters They look very similar. So you have the greedy parameters, and we looked at those in the last video. We have, if you wanted to ignore certain layers, you can do that using this parameter. We looked at this as well. The manual mode params have not changed. So if you wanted to simply specify compression ratio per layer manually, you could do that using this mode. But in addition to the standard parameters that we've already seen, there are some new parameters in channel pruning. So there is a data loader. The data loader is needed because we want to use samples to do this reconstruction step that we looked at. Specifically this last reconstruction step. So this requires data samples to flow through the model. And in addition to that, there is a parameter to specify how many reconstruction samples do you want to use. So how many samples should we pull out of the data loader per layer? There is another parameter for allowing custom downsample ops. So this is the downsample op scenario that I had explained to you that we may need in some cases. So whether should we allow the downsample ops or simply let go of that particular compression. So this is what is controlled by this flag, and the remaining parameters we have seen. So there's this additional parameter called multiplicity, which I won't go into in this video. Okay, so let's jump into the code. I'm gonna bring up editor with an empty window at the moment. And so to motivate to you that actually channel pruning and spatial SVD, the APIs are so similar, what I'm going to do is I'm going to start with the spatial SVD example that we already had, that we worked on the previous video. I'm just going to simply copy it over, and let's see how many changes we need to make, right? To make changes from spatial SVD to channel pruning. So instead of the spatial SVD parameters, we'll need channel pruning parameters. So that's one small change. So here we are taking a model, ResNet 18 from Torch Vision, pre-trained, put it on CUDA. This is the input shape of ImageNet dataset. We save a copy of the model to Onyx so that we can see it as a comparison to before and after. I think we have already done this once, so we don't need to do this again. So we'll do the greedy selection, and we are still, let's target 20% compression, or a compression ratio of 0.8, similar to what we did for spatial SVD. Let's not ignore any layers at the moment, so I will just simply remove this parameter, and this would become channel pruning parameters. This is also channel pruning parameters. We want to use the auto mode and channel pruning. And now we are, pretty much done. I think we should, just for aesthetic reasons, we should call this channel pruning parameters and change that over here as well. Okay, so just a few changes, and like by and large the code is the same. Here the compression scheme has to be channel pruning. Okay, so that's it. So now I think the editor is telling us that something it doesn't like, and what it basically is saying, oh, there were the 3 extra parameters we talked about. What about those? Okay, so we need a data loader to send it in. So in my pipeline, I happen to have a data loader. So I'm just simply going to get that. So there is data loader. And then we needed to specify the number of reconstruction samples. So in general here, something on the order of hundreds of sample is a good starting point. Maybe the more samples you do, the bigger the linear regression effort, so it'll be more compute heavy, but the better, slightly better accuracy you will see. And then I think, after a certain stage, it'll be diminishing returns. Allow custom downsample ops, let's say false for now. Okay, and then we will use the same visualization URL as before for bouquet, even though I think this time we'll probably not see that part in this video. And then once we get the compressed model, we'll print it out, print the statistics, and also export that model. Let's call it into a file called cp.onyx, and then we are going to use this utility to set the layer names in Onyx. Okay, so I hope I haven't made a mistake. If you wanted to do fine-tuning afterwards, you would essentially just call your fine-tuning routine at this point, and so on and so forth. So we are not going to do that at the moment. So let me save this and run this. And we can switch to the oh, made a mistake. And this is a pretty interesting error. So what it's telling us is, winnowing the first module of a model is not supported. So let's go back and understand what that is. So we go back to our code, and so if you see, this is a somewhat of a characteristic of channel pruning, because channel pruning is removing the input channels of a layer. So if you think about the first layer of the model, and I can show you that in Netron. So this is the ResNet 18 Onyx model. So if we go ahead and remove the input channels of this first layer, now we are changing the model in a fundamental way. We are throwing out, like if this was RGB or color depth, we are throwing out, one of those colors coming in. So this is a fundamental change to the model. Plus, I think, the way you feed data into the model, that would look like a different shape and so on. So I think in general, this is not allowed for those reasons. And so all we need to do is we have our way to ignore certain layers. So we can just simply ignore the layers. So to ignore the layers, we say modules to ignore, and that is a list. And in this case, it will be model.con1 is the layer we want to ignore, and that's it. Second time lucky, hopefully. So let's run this and look at the output over here. Okay, so it's on its way, and like as before, it's going through the eval_dict creation. So it started with now the next layer, and it started doing compression ratio 0.1 compression with that, and then compression ratio 0.2 with that. The layer in question here is the layer 10con1, which is the second layer. Let's make sure here, like this guy. Click on this is layer 10con1. So it started with this, and it's going to try different compression ratios for this. Then it's going to go to the next layer, try different compression ratios for this, and so on and so forth. So this is an time-intensive process, as we know. So I'm going to pause the video at this point and come back once this is finished. Hi, so we are back. And the compression is finished, and I'm not going to go over the same level of detail we had done in the spatial SVD compression video. So I think I want to just directly jump to the Onyx model, and I want to show you, exactly what has happened to the graph. So this is the ResNet 18 Onyx model pre-compression, and so this we are aware of. And one specific layer I would like to focus on is this layer. It's called layer 1.1.con2. And this layer has let's say 64 input channels and 64 output channels. So you can see like the output channels feed into the batch norm, which is 64. And this input channels come from this batch norm 64 channels, but also match with the output channels of this convolution, which is layer 1, con 1. Okay. So let's focus on these layers in the channel pruning model now. Okay, this is not the one I should look at. Okay, here's the one. So this is the one after channel pruning. It says resonate 18 CP. So at first glance, it looks kind of similar to the original model. Like we don't see those additional convolutions like we saw in spatial SVD. So no big difference. But let's focus on this specific layers we were looking at. Layer 1, con 2 and layer 1, con 1. And what you'll notice here is that this particular layer has been, pruned quite a bit. So it was, if you remember, 64, 64, not this SVD one, sorry. It was 64, 64, 3, 3. And that one has become, so obviously the kernel height width remained the same. But instead of 64 input channels, now this has 25 input channels. So quite a few of the input channels have been pruned. And you can see like this percolates up, like the batch norm now only needs to work on 25 channels. So this is a new batch norm compared to what was there before, right? This batch norm at 64 channels. But the batch norm here would have only 25 channels. And then it ends with this con, which had 64 output channels. Now it only has 25 output channels. And the one before it wouldn't need to change. Plus there is a split over here. But so you see the kind of changes that have been made to the graph, right? So this is what makes winnowing and channel pruning pretty intensive to figure out all these changes and make them such that the graph continues to work. So having said that, I think, you sort of saw that, invoking channel pruning is almost the same as invoking spatial SVD from an API perspective, pretty simple to invoke. One thing that we didn't cover was we've been looking at PyTorch models. We have not really looked at TensorFlow examples. And while I'm not going to actually go through a TensorFlow example with you, but I want to just show the API with you, and there are some, the API documentation also comes with some code examples. So at first cut, this is spatial SVD for TensorFlow. So it's basically compressed model for TensorFlow. And, if you look at it, it starts to look very similar to the parameters in PyTorch. And actually, I think it can be best summarized with an example. So here is spatial SVD auto mode example with TensorFlow, right? So in this particular case, they have started with a VGG16 Keras model, and the TensorFlow APIs for AIMET, they work on TensorFlow sessions. So it'll basically expect a session and give back a session. Okay, so it's kind of equivalent to the PyTorch model, giving back a PyTorch model. So if you started out with a Keras model, you could get a session because I think when you create a Keras model, it's sort of in the background, it has a TensorFlow session. So you can actually get the session, like in this case, it's going to update the default session, which we mark this session as default. And then you pass that session in to compressed model, right? If you look at the greedy selection parameters, not too much different. It looks exactly the same: target comp ratio, num comp ratio candidates, monotonic fit, saved eval scores dictionary, and then the greedy parameters, auto mode parameters, and so on and so forth. So it looks almost the same, and it's not by accident. I think we've tried to, as far as possible, try to keep the APIs very, very similar to each other, even though one is for TensorFlow and one is for PyTorch. From an implementation perspective, the underlying implementation is very different, because the way TensorFlow models are constructed and the graphs that go along with the models are very, very different from PyTorch graphs. PyTorch dynamic graphs, TensorFlow static graphs. The way you can modify the TensorFlow graphs very different from how you can modify the PyTorch model. But all those differences are under the API. The API itself tries to keep things at roughly the same level. So there are some changes. Like, for example, you will see that we require for the TensorFlow model that we require a list of input op names and list of output op names, and this is important in TensorFlow because generally, like, a TensorFlow session can have all kinds of things inside it. They can, have, because it's a static graph, you may have optimizer in the graph, and you may have things in the graph that AIMET doesn't need to know, right? It only needs to know the graph from where does it start, where do you feed in the input, and where do you expect the output as far as evaluation is concerned. It doesn't need to look at the rest of the stuff, like how the gradients are being updated. This is not something that AIMET needs to worry about. So we take in these input and output op names, and then AIMET knows where it needs to work on. But yeah, I just wanted to sort of give you a quick glimpse of the TensorFlow API. The channel pruning auto mode also looks very, very similar. Like, you will start seeing num construction samples. It uses a data set. In PyTorch, you have a data loader. In TensorFlow, you have a tf.data.dataset, roughly equivalent. You have allow custom downsample ops, so on and so forth. So I think a lot of the parameters are almost exactly the same as in PyTorch, and it's been designed that way. So whether it's channel pruning or spatial SVD, implementation very, very different, API is roughly the same. So with this, I'll conclude this video. I think I hope it was useful for you, and I hope you will watch the other videos in the series. So we have looked at the compression videos with the spatial SVD compression and channel pruning, but the remaining videos will also look at the quantization features. So thank you for watching this video. Bye.